explain about vapor compression refrigerant system. My name is Raghavan. So what we have is a problem based on vapor compression refrigerant system. So let me read the problem slowly and understand what is the given information. So firstly, a refrigeration based on vapor compression cycle operates between temperature limits of -20 and 40 degrees Celsius. The refrigerant enters the condenser as saturated vapor and leaves the condenser as saturated liquid. This is a very important information. The enthalpy and entropy values of saturated liquid and vapor at given temperatures are given in the table. So this is the table. We have the information of enthalpy and entropy for given temperatures. So now what is that we have to find? We are supposed to find out the COP and refrigeration effect. RE basically represents refrigeration effect. COP basically means coefficient of performance. So first thing is we have to decipher the information given. The information is this table, and we also have been given mass flow rate. So I have written the data here clearly. So this is the mass flow rate 0.025 kilogram per second. This will be used at the end. So given that from the table, what I am going to do is I am going to write down whatever the information I require. So what we have been asked is COP, coefficient of performance. So the coefficient of performance has this mathematical expression. So COP is equal to H1 minus H4 by H2 minus H1. So how did we get this? So H1 minus H4 essentially is the refrigeration effect, and H2 minus H1 is basically the compression work. So let me also explain the cycle. So process 1 to 2 is isentropic compression, meaning entropy remains constant. Process 2 to 3 is constant pressure and constant temperature process, that is condensation, heat rejection process. Process 3 to 4 is throttling process. Process 4 to 1 is evaporation. So this is basically essentially the refrigeration effect. We get the refrigeration effect here. Therefore, what we did is COP is numerator by denominator. Numerator is H1 minus H4 refrigeration effect by work input. Now to basically solve this, we need to evaluate all these variables. First is H1. Do we know H1? From the question we understand that H1 0.1 does not entirely stand on the saturation vapor line. So this is the saturation vapor line and this is the saturation liquid line. So in this region you have vapor plus liquid region. So 0.1 obviously is going to be in saturated liquid, vapor plus liquid region. Therefore I have to calculate dryness fraction. So that is my prime objective. So secondly, for finding out H4, I do not exactly know H4, but I do know that H4 is equal to H3 given 3 to 4 is a throttling process. So what I have done is H4 equal to H3. So this 80 kilojoule per kg has been taken from here. So this corresponds to 40 degrees Celsius. So I have taken the H4, that is basically equated to HF3. So that I will plug in the formula here. Nextly, H2 is nothing but the enthalpy associated at the end of compression. So that once again is 200 kilojoules. I have taken corresponding to 40 degrees Celsius. This is 40, this is -20. Now that we are clear, we are going to get into the calculation of dryness fraction. So how do we calculate dryness fraction? So we know that 1 to 2 is an isentropic process. In an isentropic process, entropy remains constant. S2 is nothing but Sg2 given that this is saturated vapor line. Therefore, Sg2 equal to S1, essentially it is basically combination of liquid plus vapor region. Therefore, Sf1 plus x1 multiplied by Sfg1. Sf1 is the entropy associated with liquid state and x1 is the dryness fraction. Sfg is Sg minus Sf. So Sg2 I have taken from 0.6 from the table. This is corresponding to 40 degrees given that it is 0.2. Next, Sf1 equal to 0.07 kilojoule per kg Kelvin. So I have taken this corresponding to -20 because 1 is basically the temperature corresponding to 0.1 is -20, and Sfg is nothing but the difference between Sg and Sf. So Sg is 0.366, Sf is 0.007. So now when you plug in the values of all these, you will end up with x1 equal to 0.9. So you don't have units, therefore you just have a number. So what I'm going to do is, now that we have calculated x1, we are going to calculate h1. h1 is the enthalpy associated with 0.1. So I'm just directly going to plug in the value of x1 in this formula. From equation 3, what you see here. So h1 directly substituting hf1, x1, hfg, hg minus hf. Therefore, you get h1. So h1 is basically 164 kilojoule per kg. So now the next step is once you have H1, H4 is basically found out here from the table, H2 once again is found out from the table. You are going to plug in all the values of H2, H4 and H1 in this formula, that is 1. So from 1 COP is substituted and you get 2.33. So finally the next bit here they have asked is refrigeration effect. So how do you calculate refrigeration effect? Refrigeration effect essentially is mass flow rate multiplied by enthalpy change. Mass flow rate is given as 0.0025 and enthalpy change is basically H1 minus H4. So H4 basically is HF3, therefore you have got 2.1 kilowatt. So what we have learned today is, so we have a problem where they have given mass flow rate, asked us to find given enthalpy and entropy associated with the corresponding temperatures of condenser and evaporator, and asked us to find out COP and refrigeration effect. So COP you have a formula here, refrigeration effect you have a formula here, and then H1 you have a formula here. So we have firstly calculated X1, substituted here, found out H1 has been substituted in COP, and whatever the rest of the information taken from the table, so that you will end up with COP equal to 2.33 and refrigeration effect equal to 2.1 kilowatts. Thank you.